In this video, we are going to continue practicing sketching the graph of a polynomial function given its equation. In this problem, number 32, it is a little bit different than the previous examples we did in a previous video because this is not in factored form. However, and it is easiest to graph a polynomial equation if it is in factored form. In this case, we can actually put it in factored form relatively easily. So what we're going to do is factor out the x. If I take out the x, I'll end up with this. And then we have to factor 1 minus x squared. And one thing that you should hopefully notice is that this is a difference of two squares, because 1 minus x squared is really the same as 1 squared minus x squared. And there is a rule that if you have x, some number squared minus another number squared, like a squared minus b squared, it will always be the same as a plus b times a minus b. So applying that rule here, we end up with 1 plus x times 1 minus x. All right. Now, when I have things in factored form, I always want every factor to have a positive x at the beginning. So I'm going to change the order of the 1 plus the x. And I'm going to do the same thing here, but there's a slight issue, which is that this ends up being negative x plus 1, and I don't want it to be negative x plus 1. So what am I going to do? I'm going to take negative x plus 1, and I'm going to extract negative 1. If I factor out a negative 1, this becomes positive x and minus 1. I change the sign on both sides. Okay, so these are equal to each other. If you don't believe me, do it in reverse. Do the distributive property. Negative 1 times x is negative x. Negative 1 times negative 1 is positive 1. That checks out. So I am going to do this. X plus 1, and I extract the negative 1. I factor it out, and now I'm left with x minus 1. And then I'm actually going to combine x times negative 1, and I end up with negative x. Okay. And now we have our function expressed in factored form. Okay. So let's start with step 1. Now step 1, we want to find the end behavior. And normally for the previous examples, we found what the leading coefficient is. But in this case, and we had a method that we were using because all the other examples were in factored form. But this is not in factored form. It's in standard form. So my leading coefficient will be the term that has the largest variable on the largest exponent on the variable. So our leading coefficient is equal to negative x to the third. Notice that this is negative, and my exponent is odd. That means that my end behavior will be the same as y equals negative x to the third. In fact, that's what this is. And so what does negative x to the third look like? It looks like this. On the left, it goes to positive infinity. On the right, it goes to negative infinity. So there is my end behavior. And I forgot to put step 1, so I'll put that in now. All right, let's do step 2 maybe down here. Let's find the y-intercept. And remember, the y-intercept is always equal to f of 0. And I'm not going to use the factored form here. I'm going to use this because I think this is easier. So that'll be 0 minus 0 to the third. That's just going to be 0. So I know my y-intercept is 0, 0. Next, let's look at our x-intercepts. In other words, let's find all the zeros and their multiplicity. First zero, I look at this. Okay, when is negative x equal to 0? When x is equal to 0. Right, so we have a 0 at 0. There's no exponent, so the multiplicity is 1. And that we basically already found in step 2 if you think about it. We already found that our graph intercepts the y-intercept at 0, 0. That means it intercepts the x-intercept at 0, 0 as well. Look at the next factor, x plus 1. That tells me that negative 1 is a 0, and since there's no exponent, it's of multiplicity 1 as well. Looking at the last factor, we have x minus 1, which means that positive 1 is also a 0, and this has, again, multiplicity 1. Notice that all of our multiplicities are odd numbers. That means that the graph crosses at each x-intercept. All right, let's go to step 4. Step 4, we just determine, we already did, step 4, we find the maximum number of turning points. Notice that our leading coefficient has degree 3, so the degree of f of x is equal to 3, so the max number of turning points will be 1 less than that, which is 2. And from here, we can try to graph our equation. And again, we're just trying to sketch a graph. We don't need it to be perfect for this part right here. All right, so where are our x-intercepts? They're at negative 1, 0, and 1. Our y-intercept is 0, 0. That is already covered by our x-intercepts. All right, so now once we're this far, we look at our end behavior, and I know that on the left, I start at the top at positive infinity, and I'm going to come swoop down, and notice every time I hit one of my x-intercepts, I am going to cross the x-axis. So I'm start at the left, I'm going to hit negative 1 first, I cross it, I come back to 0, I cross it, and then I come down. And notice I'm crossing at all 3. So I know this is the general look of my graph. It'll look something like this. All right, let's plug it in to Desmos and see if we get something that looks similar. So let's see, Desmos was going to be right here. And this is going to be x minus x to the third. All right, and it is looking very similar in this case. If you wanted to get really specific, you could get some extra points here. You could get the point negative 2, 6. Let's see, is there anything else? So let's maybe get some of these points. So I'm going to make my graph look a little bit nicer. I'm going to use the point negative 2, 6, and positive 2, 6 will probably be the same. That is correct. And remember, these are about at negative 1/2, a little bit past negative 1/2, and probably positive 1/2. No, I'm sorry, that's wrong. Negative, it's a little bit less than negative 1/2 is my y value at this point, at the maximum, at the local minimum, and the y value at the local maximum is a little bit past, a little bit underneath 1/2. All right. So with that in mind, I can make this graph a little bit better. So I'm going to go to -2, +6. So 1, 2, 3, 4, 5, 6 is right here. -2 is right here. And I want to go through this point. And when I go through again, the local minimum should be more like here. The local maximum should be more like here. And I should also have the point +2, -6. So 1, 2, 3, 4, 5, 6. It should be more like this. Okay? So I had the right idea with the graph, but I can make it look a little bit better. So I'm going to do that. And so I come in and I hit all of my points. Okay. Now it's not perfect, but it's definitely a little bit better. And that is how I can get the graph of this polynomial. Okay. And really the key is to sketch the graph. Try to learn how to sketch a graph on your own. And then you can use Desmos to check your work and to make your graph better. All right, we are going to do one more example, which will be this one right here. Again, this one is not factored, but that makes at least some of it easier. So step one, we're going to find the end behavior. And our lead coefficient, or the leading term, and by the way, I used the wrong word here. I always do this. It shouldn't be leading coefficient, but that's the leading term. The leading coefficient is just the number in front of the leading term. But nonetheless, the leading term here is equal to x to the third. Notice that this is positive, and the exponent is odd. So again, the end behavior will be the same as the end behavior of y equals x to the third, not surprisingly. And that looks something like this. Well, more like this. So on the left, it goes to -infinity. On the right, it goes to +infinity. And we are done. Step 2, we find the y-intercept. The way we find the y-intercept is we find f of 0, which in this case would be 0 to the third plus 2 times 0 squared minus 8 times 0, which is 0. And so our y-intercept is 0, 0. Next, we're going to do step 3, which is we want to find all the x-intercepts, also known as the zeros. Again, this is not in factored form yet, so let's try to put it in factored form. First, let's write down this in standard form. And the first thing I notice is I can factor out an x. All right, now I'm going to see if can I factor x squared plus 2x minus 8. Can I think of two numbers that multiply to get -8 and add to get +2? I actually can. That would be -4 and +2. And so this factors to this, and now I have my polynomial in factored form. So I could find all the zeros actually very easily in this case. My zeros are from this first form. If you have an x by itself, that means that your 0 is 0, and the multiplicity will be the exponent on x, but in this case there is no exponent, which means the exponent is actually 1, but we don't write that, and so our multiplicity is 1. Looking at the next factor, we have x minus 4. So that means that 4 is a 0. And again, there's no exponent on that parentheses, so our multiplicity is just 1. Last, we have x plus 2. So that means that negative 2 is a 0, and the multiplicity is, again, 1, because the exponent is missing, which means that it is being raised to the first power, this last factor. Again, just like the last example, all of our multiplicities are odd, which means the graph crosses the x-axis at each x-intercept. Step 4, how many turning points could we possibly have? Well, again, looking at our leading term is x to the third, so the degree of f of x is equal to 3, so the max number of possible turning points will just be 3 minus 1, which is 2. And we are ready to graph this one. Okay. Again, we're going to start by graphing all of our x-intercepts, which would be at negative 2, 0, and positive 4. Next, I would usually graph my y-intercept, but my y-intercept is one of my x-intercepts. Okay, so I've already graphed the y-intercept as well. It's at the origin. So now I can sketch my graph, and again, here at this point, I look at my end behavior so I know where to start. I'm going to go left to right, and I'm going to start at the bottom. And I'm just going to go through all of my x-intercepts from left to right, and I cross every time I hit one of them. So it'll look something like this. I go past that one, past this one, and I kind of missed that one. Let me try that again. All right, I can do this. There we go. Okay, it's going to look something like this. All right, let's see if we are correct. And notice that we have only 2 turning points. You have a turning point at this local maximum right here and a turning point at this local minimum right here. So we're good. Let's go ahead and use Desmos to be 100% sure and possibly to change the graph if necessary. So this was x to the third plus 2x squared minus 8x. All right, so the basics are correct. We have all of the correct intercepts at negative. Oh, did I mess up? How did I mess up? So this is why we check our work. Right here, I did my factoring wrong. This should have been positive 4 and negative 2. Because what I had before, I had negative 4 and positive 2. Those multiply to get negative 8, but when I add them, they actually add to get negative 2. So that was incorrect. I had the signs wrong. Now luckily this is not too hard to correct. So let's just correct this. We're going to make this 4 into a negative 4. Oops. And we're going to change this to a positive 2. All right. So I'm just going to put an X through these that are incorrect. And now I know that my 0 actually happens at negative 4. And my other 0 happens at positive 2. And so my graph should look more like this. Oops, let me try that one more time. Ah, geez, why did it disappear? Let me get it back. There it is. Okay. And again, this is the reason why we always check our work. It's easy for anyone, even someone who is a professor of mathematics, to make a simple mistake with positives and negatives. The important thing is not to avoid making mistakes, but to develop strategies to check your work, which is why I always check my work. So let's check our work again. Now do we have the correct x-intercepts? We have -4, 0, and +2. -4, 0, and +2. Now my graph looks pretty good. This actually happens closer to -5. If I wanted to, I could, I think that's around 1, -5. It's not perfect, but I could 1, 2, 3, 4, 5. I could say that's actually where I want that to be, that local minimum. The local maximum is all the way at negative almost 2.5 and 17. That's going to be way up in the sky up here. So I'm not going to be able to get a perfect graph without really redrawing this whole thing, but I'll get it at least a little bit better. I know this goes way up into the sky and comes down and goes back up. And again, it doesn't need to be perfect. The idea here is just to be able to sketch the graph, get a basic idea of what it should look like, and where it crosses the x-axis and the y-axis. This looks pretty close to what it's supposed to look like. It's not perfect, but it is definitely good enough for the purposes of this exercise. All right, so my apologies for making an error in that last problem, but I like to keep those in just because I do want students of mathematics to understand that people make mistakes all the time. It is so easy to mess up a positive and a negative and get them mixed up. And again, just make sure, that's why it is so important to make sure that we learn how to check our work and how to find our errors and how to get it right after we make a mistake. So I'm going to keep that in this video because hopefully that will be a good example and a place where just an example of how to learn from your mistakes. All right, that is all for now. Have a great rest of your day. I hope this video helped, and we will see you in the next video.